A molecular model shows hundreds of atoms, represented by yellow, red, black, blue, and white balls, connected together by rods to form a molecule. The molecule has a complex but very specific three-dimensional structure with rings and branches. Figure 2.1 atoms are the building blocks of molecules in the universe: air, soil, water, rocks, and also the cells of all living organisms. In this model of an organic molecule, the atoms of carbon, black, hydrogen, white, nitrogen, blue, oxygen, red, and phosphorus, yellow, are in proportional atomic size. The silver rods indicate chemical bonds. Credit: Modification of work by Christian Guthier, Chapter Outline 2.1 Atoms, Isotopes, Ions, and Molecules. The building blocks 2.2 Water 2. 3 carbon elements in various combinations comprise all matter, including living things. Some of the most abundant elements in living organisms include carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus. These form the nucleic acids, proteins, carbohydrates, and lipids that are the fundamental components of living matter. Biologists must understand these important building blocks and the unique structures of the atoms that comprise molecules, allowing for cells, tissues, organ systems, and entire organisms to form. All biological processes follow the laws of physics and chemistry, so in order to understand how biological systems work, it is important to understand the underlying physics and chemistry. For example, the flow of blood within the circulatory system follows the laws of physics that regulate the modes of fluid flow. The breakdown of the large, complex molecules of food into smaller molecules, and the conversion of these to release energy to be stored in adenosine triphosphate ATP, is a series of chemical reactions that follow chemical laws. The properties of water and the formation of hydrogen bonds are key to understanding living processes. Recognizing the properties of acids and bases is important, for example, to our understanding of the digestive process. Therefore, the fundamentals of physics and chemistry are important for gaining insight into biological processes. Learning objectives: by the end of this section, you will be able to do the following. Define matter and elements, describe the interrelationship between protons, neutrons, and electrons. Compare the ways in which electrons can be donated or shared between atoms. Explain the ways in which naturally occurring elements combine to create molecules, cells, tissues, organ systems, and organisms at its most fundamental level. Life is made up of matter. Matter is any substance that occupies space and has mass. Elements are unique forms of matter with specific chemical and physical properties that cannot break down into smaller substances by ordinary chemical reactions. There are 118 elements, but only 98 occur naturally. The remaining elements are unstable and require scientists to synthesize them in laboratories. Each element is designated by its chemical symbol, which is a single capital letter, or, when the first letter is already taken by another element, a combination of 2 letters. Some elements follow the English term for the element, such as C for carbon and Ca for calcium. Other elements, chemical symbols derive from their Latin names. For example, the symbol for sodium is Na, referring to natrium, the Latin word for sodium. The 4 elements common to all living organisms are oxygen O, carbon C, hydrogen H, and nitrogen N. In the non-living world, elements are found in different proportions, and some elements common to living organisms are relatively rare on the Earth as a whole, as Table 2.1 shows. For example, the atmosphere is rich in nitrogen and oxygen, but contains little carbon and hydrogen, while the Earth's crust, although it contains oxygen and a small amount of hydrogen, has little nitrogen and carbon. In spite of their differences in abundance, all elements and the chemical reactions between them obey the same chemical and physical laws, regardless of whether they are a part of the living or non-living world. Approximate percentage of elements in living organisms. Humans, compared to the non-living world element life. Humans, atmosphere, Earth's crust, oxygen, O, 65%, 21%, 46% carbon, C, 18% trace hydrogen, H, 10% trace 0.1% nitrogen, N, 3%, 78% trace. Table 2.1 The structure of the atom. To understand how elements come together, we must first discuss the element's smallest component or building block, the atom. An atom is the smallest unit of matter that retains all of the element's chemical properties. For example, one gold atom has all of the properties of gold, like its chemical reactivity. A gold coin is simply a very large number of gold atoms molded into the shape of a coin and contains small amounts of other elements known as impurities. We cannot break down gold atoms into anything smaller while still retaining the properties of gold. An atom is composed of two regions: the nucleus, which is in the atom's center and contains protons and neutrons. The atom's outermost region holds its electrons in orbit around the nucleus, as Figure 2.2 illustrates. Atoms contain protons, electrons, and neutrons, among other subatomic particles. The most common isotope of hydrogen, H, is the only exception and is made of one proton and one electron with no neutrons. This illustration shows that, like planets orbiting the Sun, electrons orbit the nucleus of an atom. The nucleus contains two neutrally charged neutrons and two positively charged protons represented by spheres. A single, circular orbital surrounding the nucleus contains two negatively charged electrons on opposite sides. Figure 2.2 elements, such as helium, depicted here, are made up of atoms. Atoms are made up of protons and neutrons located within the nucleus, with electrons in orbitals surrounding the nucleus. Protons and neutrons have approximately the same mass, about 1.67 times 1024 grams. Scientists arbitrarily define this amount of mass as one atomic mass unit, AMU, or 1 Dalton, as Table 2.2 shows. Although similar in mass, protons and neutrons differ in their electric charge. A proton is positively charged, whereas a neutron is uncharged. Therefore, the number of neutrons in an atom contributes significantly to its mass, but not to its charge. Electrons are much smaller in mass than protons, weighing only 9.11 times 1028 grams, or about 1/1800 of an atomic mass unit. Hence, they do not contribute much to an element's overall atomic mass. Therefore, when considering atomic mass, it is customary to ignore the mass of any electrons and calculate the atom's mass based on the number of protons and neutrons alone. Although not significant contributors to mass, electrons do contribute greatly to the atom's charge, as each electron has a negative charge equal to the proton's positive charge. In uncharged, neutral atoms, the number of electrons orbiting the nucleus is equal to the number of protons inside the nucleus. In these atoms, the positive and negative charges cancel each other out, leading to an atom with no net charge. Accounting for the sizes of protons, neutrons, and electrons, most of the atom's volume, greater than 99%, is empty space. With all this empty space, one might ask why so-called solid objects do not just pass through one another. The reason they do not is that the electrons that surround all atoms are negatively charged, and negative charges repel each other. Protons, neutrons, and electrons charge mass, AMU, location proton plus 1 nucleus neutron 0 1 nucleus electron, 1 0 orbitals table 2. 2 atomic number and mass atoms of each element contain a characteristic number of protons and electrons. The number of protons determines an element's atomic number, which scientists use to distinguish one element from another. The number of neutrons is variable, resulting in isotopes, which are different forms of the same atom that vary only in the number of neutrons they possess. Together, the number of protons and neutrons determine an element's mass number, as Figure 2.3 illustrates. Note that we disregard the small contribution of mass from electrons in calculating the mass number. We can use this approximation of mass to easily calculate how many neutrons an element has by simply subtracting the number of protons from the mass number. Since an element's isotopes will have slightly different mass numbers, scientists also determine the atomic weight, which is the calculated mean of the atomic weights of its naturally occurring isotopes. Often, the resulting number contains a fraction. For example, the atomic mass of chlorine, Cl, is 35. 45 because chlorine is composed of several isotopes, some, the majority, with atomic mass 35, 17 protons and 18 neutrons, and some with atomic mass 37, 17 protons and 20 neutrons. Visual connection carbon is indicated by its atomic symbol, A capital C carbon has the atomic number 6 and two stable isotopes, carbon-12 and carbon-13. Figure 2. 3-carbon has an atomic number of 6 and two stable isotopes with mass numbers of 12 and 13, respectively. Its relative atomic mass is 12. 11. How many neutrons do carbon-12 and carbon-13 have, respectively? Isotopes are different forms of an element that have the same number of protons but a different number of neutrons. Some elements, such as carbon, potassium, and uranium, have naturally occurring isotopes. Carbon-12 contains 6 protons, 6 neutrons, and 6 electrons. Therefore, it has a mass number of 12, 6 protons, and 6 neutrons. Carbon-14 contains 6 protons, 8 neutrons, and 6 electrons. Its atomic mass is 14, 6 protons, and 8 neutrons. These two alternate forms of carbon are isotopes. Some isotopes may emit neutrons, protons, and electrons and attain a more stable atomic configuration, lower level of potential energy. These are radioactive isotopes, or radioisotopes. Radioactive decay, carbon-14 decaying to eventually become nitrogen-14, describes the energy loss that occurs when an unstable atom's nucleus releases radiation. Evolution connection, carbon dating carbon is normally present in the atmosphere in the form of gaseous compounds like carbon dioxide and methane. Carbon-14, 14C, is a naturally occurring radioisotope that is created in the atmosphere from atmospheric 14N, nitrogen, by the addition of a neutron and the loss of a proton because of cosmic rays. This is a continuous process, so more 14C is always being created. As a living organism incorporates 14C initially as carbon dioxide fixed in the process of photosynthesis, the relative amount of 14C in its body is equal to the concentration of 14C in the atmosphere. When an organism dies, it is no longer ingesting 14C. So the ratio between 14C and 12C will decline as 14C decays gradually to 14N by a process called beta decay, electrons or positrons emission. This decay emits energy in a slow process. After approximately 5,730 years, half of the starting concentration of 14C will convert back to 14N. We call the time it takes for half of the original concentration of an isotope to decay back to its more stable form, its half-life. Because the half-life of 14C is long, scientists use it to date formerly living objects such as old bones or wood. Comparing the ratio of the 14C concentration in an object to the amount of 14C in the atmosphere, scientists can determine the amount of the isotope that has not yet decayed. On the basis of this amount, Figure 2.4 shows that we can calculate the age of the material, such as the pygmy mammoth, with accuracy if it is not much older than about 50,000 years. Other elements have isotopes with different half-lives. For example, 40K potassium-40 has a half-life of 125 billion years, and 235U uranium-235 has a half-life of about 700 million years. Through the use of radiometric dating, scientists can study the age of fossils or other remains of extinct organisms to understand how organisms have evolved from earlier species. Photo shows scientists unearthing a mammoth skeleton. Figure 2.4 scientists can determine the age of carbon-containing remains less than about 50,000 years old, such as this pygmy mammoth, using carbon dating. Credit: Bill Faulkner, NPS. Link to learn more about atoms, isotopes, and how to tell one isotope from another. Run the simulation. The periodic table organizes and displays different elements. Devised by Russian chemist Dmitry Mendeleev, 1834–1907. In 1869, the table groups elements that, although unique, share certain chemical properties with other elements. The properties of elements are responsible for their physical state at room temperature. They may be gases, solids, or liquids. Elements also have specific chemical reactivity, the ability to combine and to chemically bond with each other. In the periodic table in Figure 2.5, the elements are organized and displayed according to their atomic number, and are arranged in a series of rows and columns based on shared chemical and physical properties. In addition to providing the atomic number for each element, the periodic table also displays the element's atomic mass. Looking at carbon, for example, its symbol C and name appear, as well as its atomic number of 6 in the upper left-hand corner and its atomic mass of 12. 1. The periodic table consists of 18 groups and 7 periods. Each element has its own square. Within each square is the following information: the atomic number, the symbol, the relative atomic mass, and the name. For example, hydrogen's atomic number is 1, symbol is the letter H, relative atomic mass is 11, and name is hydrogen. 2 additional rows of elements, known as the lanthanides and actinides, are placed beneath the main table. The lanthanides include elements 57 through 71 and belong in period 7 between groups 3 and 4. The actinides include elements 89 through 98 and belong in period 8 between the same groups. These elements are placed separately to make the table more compact. For each element, the name, atomic symbol, atomic number, and atomic mass are provided. The atomic number is a whole number that represents the number of protons. The atomic mass, which is the average mass of different isotopes, is estimated to 2 decimal places. The elements are divided into 3 categories: metals, nonmetals, and metalloids. These form a diagonal line from period 2, group 13, to period 6, group 17. All elements to the left of the metalloids are metals, and all elements to the right are nonmetals. Figure 2. 5. The periodic table shows each element's atomic mass and atomic number. The atomic number appears above the symbol for the element, and the approximate atomic mass appears below it. The periodic table groups elements according to chemical properties. Scientists base the differences in chemical reactivity between the elements on the number and spatial distribution of an atom's electrons. Atoms that chemically react and bond to each other form molecules. Molecules are simply 2 or more atoms chemically bonded together. Logically, when 2 atoms chemically bond to form a molecule, their electrons, which form the outermost region of each atom, come together first as the atoms form a chemical bond. Electron shells and the Bohr model note that there is a connection between the number of protons in an element, the atomic number that distinguishes one element from another, and the number of electrons it has. In all electrically neutral atoms, the number of electrons is the same as the number of protons. Thus, each element, at least when electrically neutral, has a characteristic number of electrons equal to its atomic number. In 1913, Danish scientist Niels Bohr, 1885–1962, developed an early model of the atom. The Bohr model shows the atom as a central nucleus containing protons and neutrons, with the electrons in electron shells or energy levels at specific distances from the nucleus, as Figure 2.6 illustrates. These energy levels are designated by a number and the symbol N. For example, 1N represents the first energy level located closest to the nucleus. 3 concentric circles around the nucleus of a hydrogen atom represent principal shells. These are named 1N, 2N, and 3N in order of increasing distance from the nucleus. An electron orbits in the shell closest to the nucleus. 1N, the nucleus, is marked with an H for hydrogen. Figure 2.6. In 1913, Niels Bohr developed the Bohr model in which electrons exist within principal shells. An electron normally exists in the lowest energy shell available, which is the one closest to the nucleus. Energy from a photon of light can bump it up to a higher energy shell, but this situation is unstable, and the electron quickly decays back to the ground state. In the process, it releases a photon of light. Electrons fill orbitals in a consistent order. They first fill the orbitals closest to the nucleus, then they continue to fill orbitals of increasing energy further from the nucleus. If there are multiple orbitals of equal energy, they fill with one electron in each energy level before adding a second electron. The electrons of the outermost energy level determine the atom's energetic stability and its tendency to form chemical bonds with other atoms to form molecules. Under standard conditions, atoms fill the inner shells first, often resulting in a variable number of electrons in the outermost shell. The innermost shell has a maximum of 2 valence electrons, but the next 2 electron shells can each have 8 valence electrons. This is known as the octet rule, which states, with the exception of the innermost shell, that atoms are more stable energetically when they have 8 electrons in their valence shell, the outermost electron shell. Figure 2.7 shows examples of some neutral atoms and their electron configurations. Notice that in Figure 2.7, helium has a complete outer electron shell, with 2 electrons filling its first and only shell. Similarly, neon has a complete outer 2n shell containing 8 electrons. In contrast, chlorine and sodium have 7 and 1 in their outer shells, respectively, but theoretically they would be more energetically stable if they followed the octet rule and had 8 valence electrons. Visual connection Bohr diagrams of elements from groups 1, 14, 17, and 18, and periods 1, 2, and 3 are shown. Period 1, in which the 1n shell is filling, contains hydrogen and helium. Hydrogen, in group 1, has 1 valence electron. Helium, in group 18, has 2 valence electrons. The 1n shell holds a maximum of 2 electrons, so the shell is full and the electron configuration is stable. Period 2, in which the 2n shell is filling, contains lithium, carbon, fluorine, and neon. Lithium, in group 1, has 1 valence electron. Carbon, in group 14, has 4 valence electrons. Fluorine, in group 17, has 7 valence electrons. Neon, in group 18, has 8 valence electrons, a full octet. Period 3, in which the 3n shell is filling, contains sodium, silicon, chlorine, and argon. Sodium, in group 1, has 1 valence electron. Silicon, in group 14, has 4 valence electrons. Chlorine, in group 17, has 7 valence electrons. Argon, in group 18, has 8 valence electrons, a full octet. Figure 2.7 Bohr diagrams indicate how many electrons fill each principal shell. Group 18 elements, helium, neon, and argon, have a full outer or valence shell. A full valence shell is the most stable electron configuration. Elements in other groups have partially filled valence shells and gain or lose electrons to achieve a stable electron configuration. An atom may give, take, or share electrons with another atom to achieve a full valence shell, the most stable electron configuration. Looking at this figure, how many electrons do elements in group 1 need to lose in order to achieve a stable electron configuration? How many electrons do elements in groups 14 and 17 need to gain to achieve a stable configuration? Understanding that the periodic table's organization is based on the total number of protons and electrons helps us know how electrons distribute themselves among the shells. The periodic table is arranged in columns and rows based on the number of electrons and their location. Examine more closely some of the elements in the table's far right column in Figure 2.5. The group 18 atoms helium, He, neon, Ni, and argon, Ar, all have filled outer electron shells, making it unnecessary for them to share electrons with other atoms to attain stability. They are highly stable as single atoms. Because they are non-reactive, scientists coin them inert or noble gases. Compare this to the group 1 elements in the left-hand column. These elements, including hydrogen H, lithium Li, and sodium Na, all have 1 electron in their outermost shells. That means that they can achieve a stable configuration and a filled outer shell by donating or sharing 1 electron with another atom or a molecule, such as water. Hydrogen will donate or share its electron to achieve this configuration, while lithium and sodium will donate their electron to become stable. As a result of losing a negatively charged electron, they become positively charged ions. Group 17 elements, including fluorine and chlorine, have 7 electrons in their outmost shells. So they tend to fill this shell with an electron from other atoms or molecules, making them negatively charged ions. Group 14 elements, of which carbon is the most important to living systems, have 4 electrons in their outer shell, allowing them to make several covalent bonds, discussed below with other atoms. Thus, the periodic table's columns represent the potential shared state of these elements, outer electron shells, that is responsible for their similar chemical characteristics. Electron orbitals, although useful to explain the reactivity and chemical bonding of certain elements, the Bohr model does not accurately reflect how electrons spatially distribute themselves around the nucleus. They do not circle the nucleus like the Earth orbits the Sun, but we find them in electron orbitals. These relatively complex shapes result from the fact that electrons behave not just like particles, but also like waves. Mathematical equations from quantum mechanics, which scientists call wave functions, can predict within a certain level of probability where an electron might be at any given time. Scientists call the area where an electron is most likely to be found its orbital. Recall that the Bohr model depicts an atom's electron shell configuration. Within each electron shell are subshells, and each subshell has a specified number of orbitals containing electrons. While it is impossible to calculate exactly an electron's location, scientists know that it is most probably located within its orbital path. The letter S, P, D, and F designate the subshells. The S subshell is spherical in shape and has one orbital. Principal shell 1n has only a single s orbital, which can hold 2 electrons. Principal shell 2n has one s and one p subshell and can hold a total of 8 electrons. The p subshell has 3 dumbbell-shaped orbitals, as figure 2.8 illustrates. Subshells D and F have more complex shapes and contain 5 and 7 orbitals, respectively. We do not show these in the illustration. Principal shell 3n has s, p, and d subshells and can hold 18 electrons. Principal shell 4n has s, p, d, and f orbitals and can hold 32 electrons. Moving away from the nucleus, the number of electrons and orbitals in the energy levels increases. Progressing from one atom to the next in the periodic table, we can determine the electron structure by fitting an extra electron into the next available orbital. Illustration shows 1ns, 2ns, and 2np subshells. The 1ns subshell and 2ns subshells are both spheres, but the 2ns sphere is larger than the 1ns sphere. The 2np subshell is made up of 3 dumbbells that radiate out from the center of the atom along x, y, and z axes. Figure 2. 8 the s subshells are shaped like spheres. Both the 1n and 2n principal shells have an s orbital, but the size of the sphere is larger in the 2n orbital. Each sphere is a single orbital. 3 dumbbell-shaped orbitals comprise p subshells. Principal shell 2n has a p subshell, but shell 1 does not. The closest orbital to the nucleus, the 1's orbital, can hold up to 2 electrons. This orbital is equivalent to the Bohr model's innermost electron shell. The 1's orbital is the closest orbital to the nucleus, and it is always filled first, before any other orbital fills. Hydrogen has 1 electron, therefore, it occupies only 1 spot within the 1's orbital. We designate this as 1's 1, where the superscripted 1 refers to the 1 electron within the 1's orbital. Helium has 2 electrons, therefore, it can completely fill the 1's orbital with its 2 electrons. We designate this as 1's 2, referring to the 2 electrons of helium in the 1's orbital. On the periodic table figure 2.5, hydrogen and helium are the only 2 elements in the first row, period. This is because they only have electrons in their first shell, the 1's orbital. Hydrogen and helium are the only 2 elements that have the 1's and no other electron orbitals in the electrically neutral state. The second electron shell may contain 8 electrons. This shell contains another spherical s orbital and 3 dumbbell-shaped p orbitals, each of which can hold 2 electrons, as figure 2.8 shows. After the 1's orbital fills, the second electron shell fills, first filling its 2's orbital and then its 3 p orbitals. When filling the p orbitals, each takes a single electron. Once each p orbital has an electron, it may add a second. Lithium, Li, contains 3 electrons that occupy the first and second shells. 2 electrons fill the 1's orbital, and the third electron then fills the 2's orbital. Its electron configuration is 1's 22's 1. Neon, Ni, alternatively, has a total of 10 electrons. 2 are in its innermost 1's orbital and 8 fill its second shell, 2 each in the 2's and 3 p orbitals. Thus, it is an inert gas and energetically stable as a single atom that will rarely form a chemical bond with other atoms. Larger elements have additional orbitals, comprising the third electron shell. While the concepts of electron shells and orbitals are closely related, orbitals provide a more accurate depiction of an atom's electron configuration, because the orbital model specifies the different shapes and special orientations of all the places that electrons may occupy. Link to learning. Watch this visual animation to see the spatial arrangement of the p and s orbitals. Chemical reactions and molecules, all elements are most stable when their outermost shell is filled with electrons according to the octet rule. This is because it is energetically favorable for atoms to be in that configuration, and it makes them stable. However, since not all elements have enough electrons to fill their outermost shells, atoms form chemical bonds with other atoms, thereby obtaining the electrons they need to attain a stable electron configuration. When two or more atoms chemically bond with each other, the resultant chemical structure is a molecule. The familiar water molecule, H2O, consists of two hydrogen atoms and one oxygen atom. These bond together to form water, as Figure 2.9 illustrates. Atoms can form molecules by donating, accepting, or sharing electrons to fill their outer shells. In the first image, an oxygen atom is shown with 6 valence electrons. 4 of these valence electrons form pairs at the top and right sides of the valence shell. The other 2 electrons are alone on the bottom and left sides. A hydrogen atom sits next to each the lone electron of the oxygen. Each hydrogen has only 1 valence electron. An arrow indicates that a reaction takes place. After the reaction, in the second image, each unpaired electron in the oxygen joins an electron from one of the hydrogen atoms, so that the valence rings are now connected together. The bond that forms between oxygen and hydrogen can also be represented by a dash. Figure 2. 2 or more atoms may bond with each other to form a molecule. When 2 hydrogens and an oxygen share electrons via covalent bonds, it forms a water molecule. Chemical reactions occur when 2 or more atoms bond together to form molecules, or when bonded atoms break apart. Scientists call the substances used in the beginning of a chemical reaction reactants, usually on the left side of a chemical equation. And we call the substances at the end of the reaction products, usually on the right side of a chemical equation. We typically draw an arrow between the reactants and products to indicate the chemical reaction's direction. This direction is not always a one-way street. To create the water molecule above, the chemical equation would be 2H plus O right arrow H2O. An example of a simple chemical reaction is breaking down hydrogen peroxide molecules, each of which consists of 2 hydrogen atoms bonded to 2 oxygen atoms, H2O2. The reactant hydrogen peroxide breaks down into water, containing 1 oxygen atom bound to 2 hydrogen atoms, H2O, and oxygen, which consists of 2 bonded oxygen atoms, O2. In the equation below, the reaction includes 2 hydrogen peroxide molecules and 2 water molecules. This is an example of a balanced chemical equation, wherein each element's number of atoms is the same on each side of the equation. According to the law of conservation of matter, the number of atoms before and after a chemical reaction should be equal, such that no atoms are, under normal circumstances, created or destroyed. 2H2O2, hydrogen peroxide, right arrow 2H2O water plus O2 oxygen. Even though all of the reactants and products of this reaction are molecules, each atom remains bonded to at least one other atom. In this reaction, only hydrogen peroxide and water are representatives of compounds. They contain atoms of more than one type of element. Molecular oxygen, alternatively, as Figure 2.10 shows, consists of 2 doubly bonded oxygen atoms and is not classified as a compound but as a homonuclear molecule. 2 oxygen atoms are shown side by side. Each has 6 valence electrons, 2 that are paired and 2 that are unpaired. An arrow indicates that a reaction takes place. After the reaction, the 4 unpaired electrons join to form a double bond. This double bond can also be depicted by an equal sign between 2 O's. Figure 2.10, a double bond joins the oxygen atoms in an O2 molecule. Some chemical reactions, such as the one above, can proceed in one direction until they expend all the reactants. The equations that describe these reactions contain a unidirectional arrow and are irreversible. Reversible reactions are those that can go in either direction. In reversible reactions, reactants turn into products, but when the product's concentration goes beyond a certain threshold, characteristic of the particular reaction, some of these products convert back into reactants. At this point, product and reactant designations reverse. This back and forth continues until a certain relative balance between reactants and products occurs, a state called equilibrium, a chemical equation with a double-headed arrow pointing towards both the reactants and products often denote these reversible reaction situations. For example, in human blood, excess hydrogen ions, H+, bind to bicarbonate ions, HCO3, forming an equilibrium state with carbonic acid, H2CO3. If we added carbonic acid to this system, some of it would convert to bicarbonate and hydrogen ions. HCO3- plus H plus left H2CO3. However, biological reactions rarely obtain equilibrium because the concentrations of the reactants or products or both are constantly changing, often with one reaction's product a reactant for another. To return to the example of excess hydrogen ions in the blood, forming carbonic acid will be the reaction's major direction. However, the carbonic acid can also leave the body as carbon dioxide gas via exhalation instead of converting back to bicarbonate ion, thus driving the reaction to the right by the law of mass action. These reactions are important for maintaining homeostasis in our blood. HCO3- plus H plus left right arrow H2CO, 3 left right arrow CO2 plus H2O. Ions in ionic bonds. Some atoms are more stable when they gain or lose an electron, or possibly two, and form ions. This fills their outermost electron shell and makes them energetically more stable. Because the number of electrons does not equal the number of protons, each ion has a net charge. Cations are positive ions that form by losing electrons. Negative ions form by gaining electrons, which we call anions. We designate anions by their elemental name and change the ending to "ide." Thus, the anion of chlorine is chloride, and the anion of sulfur is sulfide. Scientists refer to this movement of electrons from one element to another as electron transfer. As Figure 211 illustrates, sodium, Na, only has one electron in its outer electron shell. It takes less energy for sodium to donate that one electron than it does to accept 7 more electrons to fill the outer shell. If sodium loses an electron, it now has 11 protons, 11 neutrons, and only 10 electrons, leaving it with an overall charge of +1. We now refer to it as a sodium ion. Chlorine, Cl, in its lowest energy state, called the ground state, has 7 electrons in its outer shell. Again, it is more energy efficient for chlorine to gain 1 electron than to lose 7. Therefore, it tends to gain an electron to create an ion with 17 protons, 17 neutrons, and 18 electrons, giving it a net negative, 1 charge. We now refer to it as a chloride ion. In this example, sodium will donate its 1 electron to empty its shell, and chlorine will accept that electron to fill its shell. Both ions now satisfy the octet rule and have complete outermost shells. Because the number of electrons is no longer equal to the number of protons, each is now an ion and has a +1 sodium cation or 1 chloride anion charge. Note that these transactions can normally only take place simultaneously. In order for a sodium atom to lose an electron, it must be in the presence of a suitable recipient like a chlorine atom. A sodium and a chlorine atom sit side by side. The sodium atom has 1 valence electron, and the chlorine atom has 7. 6 of chlorine's electrons form pairs at the top, bottom, and right sides of the valence shell. The 7th electron sits alone on the left side. The sodium atom transfers its valence electron to chlorine's valence shell, where it pairs with the unpaired left electron. An arrow indicates a reaction takes place. After the reaction takes place, the sodium becomes a cation with a charge of +1 and an empty valence shell, while the chlorine becomes an anion with a charge of -1 and a full valence shell containing 8 electrons. Figure 2:11 in the formation of an ionic compound, metals lose electrons and nonmetals gain electrons to achieve an octet. Ionic bonds form between ions with opposite charges. For instance, positively charged sodium ions and negatively charged chloride ions bond together to make crystals of sodium chloride, or table salt, creating a crystalline molecule with 0 net charge. Physiologists refer to certain salts as electrolytes, including sodium, potassium, and calcium, ions necessary for nerve impulse conduction, muscle contractions, and water balance. Many sports drinks and dietary supplements provide these ions to replace those lost from the body via sweating during exercise. Covalent bonds and other bonds and interactions. Another way to satisfy the octet rule is by sharing electrons between atoms to form covalent bonds. These bonds are stronger and much more common than ionic bonds in the molecules of living organisms. We commonly find covalent bonds in carbon-based organic molecules, such as our DNA and proteins. We also find covalent bonds in inorganic molecules like H2O, CO2, and O2. The bonds may share 1, 2, or 3 pairs of electrons, making single, double, and triple bonds, respectively. The more covalent bonds between two atoms, the stronger their connection. Thus, triple bonds are the strongest. The strength of different levels of covalent bonding is one of the main reasons living organisms have a difficult time in acquiring nitrogen for use in constructing their molecules, even though molecular nitrogen, N2, is the most abundant gas in the atmosphere. Molecular nitrogen consists of two nitrogen atoms triple bonded to each other, and, as with all molecules, sharing these 3 pairs of electrons between the two nitrogen atoms allows for filling their outer electron shells, making the molecule more stable than the individual nitrogen atoms. This strong triple bond makes it difficult for living systems to break apart this nitrogen in order to use it as constituents of proteins and DNA. Forming water molecules provides an example of covalent bonding. Covalent bonds bind the hydrogen and oxygen atoms that combine to form water molecules, as Figure 2.9 shows. The electron from the hydrogen splits its time between the hydrogen atom's incomplete outer shell and the oxygen atom's incomplete outer shell. To completely fill the oxygen's outer shell, which has 6 electrons but which would be more stable with 8, 2 electrons, one from each hydrogen atom, are needed. Hence, the well-known formula H2O. The two elements share the electrons to fill the outer shell of each, making both elements more stable. Link to learning. View this short video to see an animation of ionic and covalent bonding. Polar covalent bonds. There are 2 types of covalent bonds, polar and nonpolar. In a polar covalent bond, Figure 2.12 shows atoms unequally share the electrons as the electrons are attracted more to one nucleus than the other. Because of the unequal electron distribution between the atoms of different elements, a slightly positive delta plus or slightly negative delta charge develops. This partial charge is an important property of water and accounts for many of its characteristics. Water is a polar molecule, with the hydrogen atoms acquiring a partial positive charge and the oxygen a partial negative charge. This occurs because the oxygen atom's nucleus is more attractive to the hydrogen atom's electrons than the hydrogen nucleus is to the oxygen's electrons. Thus, oxygen has a higher electronegativity than hydrogen, and the shared electrons spend more time near the oxygen nucleus than the hydrogen atom's nucleus, giving the oxygen and hydrogen atoms slightly negative and positive charges, respectively. Another way of stating this is that the probability of finding a shared electron near an oxygen nucleus is more likely than finding it near a hydrogen nucleus. Either way, the atom's relative electronegativity contributes to developing partial charges whenever one element is significantly more electronegative than the other. And the charges that these polar bonds generate may then be used to form hydrogen bonds based on the attraction of opposite partial charges. Hydrogen bonds, which we discuss in detail below, are weak bonds between slightly positively charged hydrogen atoms to slightly negatively charged atoms in other molecules. Since macromolecules often have atoms within them that differ in electronegativity, polar bonds are often present in organic molecules. Nonpolar covalent bonds. Nonpolar covalent bonds form between two atoms of the same element or between different elements that share electrons equally. For example, molecular oxygen, O2, is nonpolar because the electrons distribute equally between the two oxygen atoms. Figure 2.12 also shows another example of a nonpolar covalent bond, methane, CH4. Carbon has 4 electrons in its outermost shell and needs 4 more to fill it. It obtains these 4 from 4 hydrogen atoms, each atom providing 1, making a stable outer shell of 8 electrons. Carbon and hydrogen do not have the same electronegativity but are similar. Thus, nonpolar bonds form. The hydrogen atoms each need one electron for their outermost shell, which is filled when it contains two electrons. These elements share the electrons equally among the carbons and the hydrogen atoms, creating a nonpolar covalent molecule. Table compares water, methane, and carbon dioxide molecules. In water, oxygen has a stronger pull on electrons than hydrogen, resulting in a polar covalent OH bond. Likewise, in carbon dioxide, the oxygen has a stronger pull on electrons than carbon, and the bond is polar covalent. However, water has a bent shape because two lone pairs of electrons push the hydrogen atoms together, so the molecule is polar. By contrast, carbon dioxide has two double bonds that repel each other, resulting in a linear shape. The polar bonds in carbon dioxide cancel each other out, resulting in a nonpolar molecule. In methane, the bond between carbon and hydrogen is nonpolar, and the molecule is a symmetrical tetrahedron with hydrogens spaced as far apart as possible on the three-dimensional sphere. Since methane is symmetrical with nonpolar bonds, it is a nonpolar molecule. Figure 2:12. Whether a molecule is polar or nonpolar depends both on bond type and molecular shape. Both water and carbon dioxide have polar covalent bonds, but carbon dioxide is linear, so the partial charges on the molecule cancel each other out. Hydrogen bonds and van der Waals interactions. Ionic and covalent bonds between elements require energy to break. Ionic bonds are not as strong as covalent, which determines their behavior in biological systems. However, not all bonds are ionic or covalent bonds. Weaker bonds can also form between molecules. Two weak bonds that occur frequently are hydrogen bonds and van der Waals interactions. Without these two types of bonds, life as we know it would not exist. Hydrogen bonds provide many of the critical, life-sustaining properties of water and also stabilize the structures of proteins and DNA, the building block of cells. When polar covalent bonds containing hydrogen form, the hydrogen in that bond has a slightly positive charge, because hydrogen's electron is pulled more strongly toward the other element and away from the hydrogen. Because the hydrogen is slightly positive, it will be attracted to neighboring negative charges. When this happens, a weak interaction occurs between the hydrogen's delta plus from one molecule and the molecule's delta, charge on another molecule with the more electronegative atoms, usually oxygen. Scientists call this interaction a hydrogen bond. This type of bond is common and occurs regularly between water molecules. Individual hydrogen bonds are weak and easily broken. However, they occur in very large numbers in water and in organic polymers, creating a major force in combination. Hydrogen bonds are also responsible for zipping together the DNA double helix. Like hydrogen bonds, van der Waals interactions are weak attractions or interactions between molecules. Van der Waals attractions can occur between any two or more molecules and are dependent on slight fluctuations of the electron densities, which are not always symmetrical around an atom. For these attractions to happen, the molecules need to be very close to one another. These bonds, along with ionic, covalent, and hydrogen bonds, contribute to the protein's three-dimensional structure in our cells that is necessary for their proper function. Career connection. Pharmaceutical chemist. Pharmaceutical chemists are responsible for developing new drugs and trying to determine the mode of action of both old and new drugs. They are involved in every step of the drug development process. We can find drugs in the natural environment, or we can synthesize them in the laboratory. In many cases, chemists change potential drugs from nature chemically in the laboratory to make them safer and more effective, and sometimes synthetic versions of drugs substitute for the version we find in nature. After a drug's initial discovery or synthesis, the chemist then develops the drug, perhaps chemically altering it, testing it to see if it is toxic, and then designing methods for efficient large-scale production. Then, the process of approving the drug for human use begins. In the United States, the Food and Drug Administration, FDA, handles drug approval. This involves a series of large-scale experiments using human subjects to ensure the drug is not harmful and effectively treats the condition for which it is intended. This process often takes several years and requires the participation of physicians and scientists, in addition to chemists, to complete testing and gain approval. An example of a drug that was originally discovered in a living organism is paclitaxel, Taxol, an anti-cancer drug used to treat breast cancer. This drug was discovered in the bark of the Pacific yew tree. Another example is aspirin, originally isolated from willow tree bark. Finding drugs often means testing hundreds of samples of plants, fungi, and other forms of life to see if they contain any biologically active compounds. Sometimes, traditional medicine can give modern medicine clues as to where to find an active compound. For example, mankind has used willow bark to make medicine for thousands of years, dating back to ancient Egypt. However, it was not until the late 1800s that scientists and pharmaceutical companies purified and marketed the aspirin molecule, acetylsalicylic acid, for human use. Occasionally, drugs developed for one use have unforeseen effects that allow usage in other, unrelated ways. For example, scientists originally developed the drug minoxidil, Rogaine, to treat high blood pressure. When tested on humans, researchers noticed that individuals taking the drug would grow new hair. Eventually, the pharmaceutical company marketed the drug to people with baldness to restore lost hair. Finally, a pharmaceutical chemist may discover negative effects or even lack of effects. In the early 1960s, inventors, doctors, and even a U.S. senator claimed anti-cancer properties of a new drug, Crebiozin, and began to market and sell it aggressively. Through the process of infrared spectrometry, FDA chemist Alma Levant Hayden and her team discovered that the miracle drug was nothing more than a common compound called creatine. A pharmaceutical chemist's career may involve detective work, experimentation, and drug development, all with the goal of making human beings healthier. Learning objectives. By the end of this section, you will be able to do the following. Describe the properties of water that are critical to maintaining life. Explain why water is an excellent solvent. Provide examples of water's cohesive and adhesive properties. Discuss the role of acids, bases, and buffers in homeostasis. Why do scientists spend time looking for water on other planets? Why is water so important? It is because water is essential to life as we know it. Water is one of the more abundant molecules and the one most critical to life on Earth. Water comprises approximately 60–70% of the human body. Without it, life as we know it simply would not exist. The polarity of the water molecule and its resulting hydrogen bonding make water a unique substance with special properties that are intimately tied to the processes of life. Life originally evolved in a watery environment, and most of an organism's cellular chemistry and metabolism occur inside the watery contents of the cell's cytoplasm. Special properties of water are its high heat capacity and heat of vaporization, its ability to dissolve polar molecules, its cohesive and adhesive properties, and its dissociation into ions that leads to generating pH. Understanding these characteristics of water helps to elucidate its importance in maintaining life. Water's polarity. One of water's important properties is that it is composed of polar molecules. The hydrogen and oxygen within water molecules, H2O, form polar covalent bonds. While there is no net charge to a water molecule, water's polarity creates a slightly positive charge on hydrogen and a slightly negative charge on oxygen, contributing to water's properties of attraction. Water generates charges because oxygen is more electronegative than hydrogen, making it more likely that a shared electron would be near the oxygen nucleus than the hydrogen nucleus, thus generating the partial negative charge near the oxygen. As a result of water's polarity, each water molecule attracts other water molecules because of the opposite charges between water molecules, forming hydrogen bonds. Water also attracts or is attracted to other polar molecules and ions. We call a polar substance that interacts readily with or dissolves in water hydrophilic. Hydro equals water. Philic equals loving. In contrast, nonpolar molecules such as oils and fats do not interact well with water, as Figure 213 shows. A good example of this is vinegar and oil salad dressing, an acidic water solution. We call such nonpolar compounds hydrophobic. Hydro equals water. Phobic, fearing. 4 water molecules are shown with hydrogen bonds between them. The hydrogen bonds are dotted lines connecting the hydrogen atom from one molecule with an oxygen atom from another molecule. Figure 2.13. The polarity of water. The polarity of water is due to the differing electronegativities of hydrogen and oxygen. As a consequence, hydrogen bonds are formed when the slightly negative oxygen on one water molecule is attracted to the slightly positive hydrogen of another water molecule. Credit Rao A. Fletcher, S. Ryan, K. Tagg, A. and Hawkins, A. Department of Biology, Texas A&M University. Water states, gas, liquid, and solid. The formation of hydrogen bonds is an important quality of the liquid water that is crucial to life as we know it. As water molecules make hydrogen bonds with each other, water takes on some unique chemical characteristics compared to other liquids, and since living things have a high water content, understanding these chemical features is key to understanding life. In liquid water, hydrogen bonds constantly form and break as the water molecules slide past each other. The water molecule's motion, kinetic energy, causes the bonds to break due to the heat contained in the system. When the heat rises as water boils, the water molecule's higher kinetic energy causes the hydrogen bonds to break completely and allows water molecules to escape into the air as gas, steam, or water vapor. Alternatively, when water temperature reduces and water freezes, the water molecules form a crystalline structure maintained by hydrogen bonding. There is not enough energy to break the hydrogen bonds that makes ice less dense than liquid water, a phenomenon that we do not see when other liquids solidify. Water's lower density in its solid form is due to the way hydrogen bonds orient as they freeze. The water molecules push farther apart compared to liquid water. With most other liquids, solidification when the temperature drops includes lowering kinetic energy between molecules, allowing them to pack even more tightly than in liquid form and giving the solid a greater density than the liquid. The lower density of ice, as Figure 2.14 depicts, causes it to float at the surface of liquid water, such as in an iceberg or ice cubes in a glass of water. In lakes and ponds, ice will form on the water's surface, creating an insulating barrier that protects the animals and plant life in the pond from freezing. Without this insulating ice layer, plants and animals living in the pond would freeze in the solid block of ice and could not survive. The expansion of ice relative to liquid water causes the detrimental effect of freezing on living organisms. The ice crystals that form upon freezing rupture the delicate membranes essential for living cells to function, irreversibly damaging them. Cells can only survive freezing if another liquid like glycerol temporarily replaces the water in them. Illustration A shows the molecular structure of ice. The water molecules are arranged in hexagons and are bonded together with hydrogen bonds. The hexagonal arrangements have a good deal of space between them. Image B shows ice floes floating on ocean water near a mountain range that rises out of the water. Figure 2.14 hydrogen bonding makes ice less dense than liquid water. The lattice structure of ice makes it less dense than the liquid water's freely flowing molecules, enabling it to float on water. Credit A. Modification of work by Jane Whitney, image created using visual molecular dynamics, VMD, Software 1. Credit B. Modification of work by Carlos Pont. Link to learning. Click here to see a 3D animation of an ice lattice structure. Water's high heat capacity. Water's high heat capacity is a property that hydrogen bonding among water molecules causes. Water has the highest specific heat capacity of any liquid. We define specific heat as the amount of heat 1 gram of a substance must absorb or lose to change its temperature by 1 degree Celsius. For water, this amount is 1 calorie. It therefore takes water a long time to heat and a long time to cool. In fact, water's specific heat capacity is about 5 times more than that of sand. This explains why the land cools faster than the sea. Due to its high heat capacity, warm-blooded animals use water to more evenly disperse heat in their bodies. It acts in a similar manner to a car's cooling system, transporting heat from warm places to cool places, causing the body to maintain a more even temperature. Water's heat of vaporization. Water also has a high heat of vaporization, the amount of energy required to change 1 gram of a liquid substance to a gas. A considerable amount of heat energy, 586 cal, is required to accomplish this change in water. This process occurs on the water's surface. As liquid water heats up, hydrogen bonding makes it difficult to separate the liquid water molecules from each other, which is required for it to enter its gaseous phase, steam. As a result, water acts as a heat sink or heat reservoir and requires much more heat to boil than does a liquid such as ethanol, grain alcohol, whose hydrogen bonding with other ethanol molecules is weaker than water's hydrogen bonding. Eventually, as water reaches its boiling point of 100 degrees Celsius, 212 degrees Fahrenheit, the heat is able to break the hydrogen bonds between the water molecules, and the kinetic energy, motion, between the water molecules allows them to escape from the liquid as a gas. Even when below its boiling point, water's individual molecules acquire enough energy from other water molecules such that some surface water molecules can escape and vaporize. We call this process evaporation. The fact that hydrogen bonds need to be broken for water to evaporate means that bonds use a substantial amount of energy in the process. As the water evaporates, energy is taken up by the process, cooling the environment where the evaporation is taking place. In many living organisms, including in humans, the evaporation of sweat, which is 90% water, allows the organism to cool so that it can maintain homeostasis of body temperature. Water's solvent properties. Since water is a polar molecule with slightly positive and slightly negative charges, ions and polar molecules can readily dissolve in it. Therefore, we refer to water as a solvent, a substance capable of dissolving other polar molecules and ionic compounds. The charges associated with these molecules will form hydrogen bonds with water, surrounding the particle with water molecules. We refer to this as a sphere of hydration, or a hydration shell, as Figure 2.15 illustrates, and serves to keep the particles separated or dispersed in the water. When we add ionic compounds to water, the individual ions react with the water molecule's polar regions, and their ionic bonds are disrupted in the process of dissociation. Dissociation occurs when atoms or groups of atoms break off from molecules and form ions. Consider table salt, NaCl, or sodium chloride. When we add NaCl crystals to water, the NaCl molecules dissociate into Na+ and Cl ions, and spheres of hydration form around the ions, as Figure 2.15 illustrates. The partially negative charge of the water molecule's oxygen surrounds the positively charged sodium ion. The hydrogen's partially positive charge on the water molecule surrounds the negatively charged chloride ion. When sodium chloride dissolves in water, the positively charged sodium ions interact with the oxygen of water, and the negatively charged chlorine ions interact with the hydrogen of water. A negatively charged chlorine ion is shown surrounded by water molecules whose hydrogen atoms are oriented inward toward the chlorine ion. A positively charged sodium ion is shown surrounded by water molecules whose oxygen atoms are oriented inward toward the sodium ion. Chloride dissolves in water, the positively charged sodium ions interact with the oxygen of water, and the negatively charged chlorine ions interact with the hydrogen of water. Figure 2.15 When we mix table salt, NaCl, and water, it forms spheres of hydration around the ions. Water's cohesive and adhesive properties. Have you ever filled a glass of water to the very top and then slowly added a few more drops? Before it overflows, the water forms a dome-like shape above the rim of the glass. This water can stay above the glass because of the property of cohesion. In cohesion, water molecules are attracted to each other because of hydrogen bonding, keeping the molecules together at the liquid-gas, water-air interface, although there is no more room in the glass. Cohesion allows for surface tension, the capacity of a substance to withstand rupturing when placed under tension or stress. This is also why water forms droplets when on a dry surface rather than flattening by gravity. When we place a small scrap of paper onto a water droplet, the paper floats on top even though paper is denser, heavier than the water. Cohesion and surface tension keep the water molecule's hydrogen bonds intact and support the item floating on the top. It's even possible to float a needle on top of a glass of water if you place it gently without breaking the surface tension, as Figure 2.16 shows. A photograph shows a needle floating at the surface of a glass of water. Though the needle floats, it appears to be slightly sinking below the surface. Figure 2:16. A needle's weight pulls the surface downward. At the same time, the surface tension pulls it up, suspending it on the water's surface, preventing it from sinking. Notice the indentation in the water around the needle. Credit Corey's anchor. These cohesive forces are related to water's property of adhesion, or the attraction between water molecules and other molecules. This attraction is sometimes stronger than water's cohesive forces, especially when the water is exposed to charged surfaces, such as those on the inside of thin glass tubes known as capillary tubes. We observe adhesion when water climbs up the tube placed in a glass of water. Notice that the water appears to be higher on the tube's sides than in the middle. This is because the water molecules are attracted to the capillary's charged glass walls more than they are to each other and therefore adhere to it. We call this type of adhesion capillary action, as Figure 2:17 illustrates. A thin, hollow tube sits in a beaker of water. The water level inside the tube is higher than the water level in the beaker due to capillary action. Figure 2:17, the adhesive forces exerted by the glass internal surface exceeding the cohesive forces between the water molecules themselves causes capillary action in a glass tube. Credit Modification of work by Pearson Scott Forsman, donated to the Wikimedia Foundation. Why are cohesive and adhesive forces important for life? Cohesive and adhesive forces are important for transporting water from the roots to the leaves in plants. These forces create a pull on the water column. This pull results from the tendency of water molecules evaporating on the plant's surface to stay connected to water molecules below them, and so they are pulled along. Plants use this natural phenomenon to help transport water from their roots to their leaves. Without these properties of water, plants would be unable to receive the water and the dissolved minerals they require. In another example, insects such as the water strider, as Figure 2:18 shows, use the water surface tension to stay afloat on the water's surface layer and even mate there. Photo shows an insect with long, thin legs standing on the surface of water. Figure 2:18 water's cohesive and adhesive properties allow this water strider, Jerris sp, to stay afloat. Credit Tim Vickers. pH buffers acids and bases. The pH of a solution indicates its acidity or basicity. H2O, L, left right arrow H plus AC plus O minus, AC. You may have used litmus or pH paper, filter paper treated with a natural water-soluble dye for use as a pH indicator. It tests how much acid, acidity, or basicity exists in a solution. You might have even used some to test whether the water in a swimming pool is properly treated. In both cases, the pH test measures hydrogen ions concentration in a given solution. Hydrogen ions spontaneously generate in pure water by the dissociation ionization of a small percentage of water molecules into equal numbers of hydrogen, H+, ions and hydroxide, OH, ions. While the hydroxide ions are kept in solution by their hydrogen bonding with other water molecules, the hydrogen ions, consisting of naked protons, immediately attract to unionized water molecules, forming hydronium ions, H3O+. Still, by convention, scientists refer to hydrogen ions and their concentration as if they were free in this state in liquid water. The concentration of hydrogen ions dissociating from pure water is 1 × 10⁷ moles H+ ions per liter of water. Moles mol are a way to express the amount of a substance, which can be atoms, molecules, ions, etc. 1 mole represents the atomic weight of a substance, expressed in grams, which equals the amount of the substance containing as many units as there are atoms in 12 grams of 12C. Mathematically, 1 mole is equal to 6, 2 × 10⁻³ particles of the substance. Therefore, 1 mole of water is equal to 6, 2 × 10⁻³ water molecules. We calculate the pH as the negative of the base 10 logarithm of this concentration. The log 10 of 1 × 10⁷ is 0, and the negative of this number, indicated by the P of pH, yields a pH of 7. 0, which is also a neutral pH, the pH inside of human cells and blood, are examples of 2 body areas where near-neutral pH is maintained. Non-neutral pH readings result from dissolving acids or bases in water. Using the negative logarithm to generate positive integers, high concentrations of hydrogen ions yield a low pH number. Whereas low levels of hydrogen ions result in a high pH in acid, is a substance that increases hydrogen ions, H+, concentration in a solution, usually by having one of its hydrogen atoms dissociate. A base provides either hydroxide ions, OH, or other negatively charged ions that combine with hydrogen ions, reducing their concentration in the solution and thereby raising the pH. In cases where the base releases hydroxide ions, these ions bind to free hydrogen ions, generating new water molecules. The stronger the acid, the more readily it donates H+. For example, hydrochloric acid, HCl, completely dissociates into hydrogen and chloride ions and is highly acidic. Whereas the acids in tomato juice or vinegar do not completely dissociate and are weak acids. Conversely, strong bases are those substances that readily donate OH or take up hydrogen ions. Sodium hydroxide, NaOH, and many household cleaners are highly alkaline and give up OH rapidly when we place them in water, thereby raising the pH. An example of a weak basic solution is seawater, which has a pH near 8. This is close enough to a neutral pH that marine organisms have adapted in order to live and thrive in a saline environment. The pH scale is, as we previously mentioned, an inverse logarithm and ranges from 0 to 14, figure 219. Anything below 70, ranging from 0 to 6. 9 is acidic, and anything above 70, from 7 to 14, is alkaline. Extremes in pH in either direction from 70 are usually inhospitable to life. The pH inside cells, 6, 8, and the pH in the blood, 7.4, are both very close to neutral. However, the environment in the stomach is highly acidic, with a pH of 1 to 2. As a result, how do stomach cells survive in such an acidic environment? How do they homeostatically maintain the near-neutral pH inside them? The answer is that they cannot do it and are constantly dying. The stomach constantly produces new cells to replace dead ones, which stomach acids digest. Scientists estimate that the human body completely replaces the stomach lining every 7 to 10 days. The lowercase p uppercase h scale, which ranges from 0 to 14, sits next to a bar with the colors of the rainbow. The pH of common substances are given. These include gastric acid with a pH around 1, lemon juice with a pH around 2, orange juice with a pH around 3, tomato juice with a pH around 4, black coffee with a pH around 5, urine with a pH around 6, distilled water with a pH around 7, sea water with a pH around 8, baking soda with a pH around 9, milk of magnesia with a pH around 10, ammonia solution with a pH around 11, soapy water with a pH around 12, and bleach with a pH around 13. Figure 2:19. The pH scale measures hydrogen ions, H+ concentration in a solution. Credit: modification of work by Edward Stevens. Link to learning. Watch this video for a straightforward explanation of pH and its logarithmic scale. How can organisms whose bodies require a near-neutral pH ingest acidic and basic substances, a human drinking orange juice, for example, and survive? Buffers are the key. Buffers readily absorb excess H+ or OH, keeping the body's pH carefully maintained in the narrow range required for survival. Maintaining a constant blood pH is critical to a person's well-being. The buffer maintaining the pH of human blood involves carbonic acid, H2CO3, bicarbonate ion, HCO3, and carbon dioxide, CO2. When bicarbonate ions combine with free hydrogen ions and become carbonic acid, it removes hydrogen ions and moderates pH changes. Similarly, as Figure 2:20 shows, excess carbonic acid can convert to carbon dioxide gas, which we exhale through the lungs. This prevents too many free hydrogen ions from building up in the blood and dangerously reducing the blood's pH. Likewise, if too much OH enters into the system, carbonic acid will combine with it to create bicarbonate. Lowering the pH without this buffer system, the body's pH would fluctuate enough to put survival in jeopardy. an uppercase H subscript 2 baseline uppercase O molecule can combine with an uppercase C uppercase O subscript 2 baseline molecule to form H subscript 2 baseline C O subscript 3 baseline, or carbonic acid. A proton may dissociate from H subscript 2 baseline CO subscript 3 baseline, forming bicarbonate, or HCO subscript 3 baseline superscript negative in the process. The reaction is reversible so that if acid is added, protons combined with bicarbonate to form carbonic acid. Figure 2.20. This diagram shows the body's buffering of blood pH levels. The blue arrows show the process of raising pH as more CO2 is made. The purple arrows indicate the reverse process, the lowering of pH as more bicarbonate is created. Other examples of buffers are antacids that some people use to combat excess stomach acid. Many of these over-the-counter medications work in the same way as blood buffers, usually with at least one ion capable of absorbing hydrogen and moderating pH, bringing relief to those who suffer heartburn after eating. Water's unique properties that contribute to this capacity to balance pH, as well as water's other characteristics, are essential to sustaining life on Earth. Link to learning. To learn more about water, visit the U.S. Geological Survey Water Science for Schools All About Water website. Learning objectives. By the end of this section, you will be able to do the following. Explain why carbon is important for life. Describe the role of functional groups in biological molecules. Many complex molecules called macromolecules, such as proteins, nucleic acids, RNA and DNA, carbohydrates, and lipids comprise cells. The macromolecules are a subset of organic molecules, any carbon-containing liquid, solid, or gas that are especially important for life. The fundamental component for all of these macromolecules is carbon. The carbon atom has unique properties that allow it to form covalent bonds to as many as 4 different atoms, making this versatile element ideal to serve as the basic structural component, or backbone, of the macromolecules. Individual carbon atoms have an incomplete outermost electron shell. With an atomic number of 6 electrons and 6 protons, the first 2 electrons fill the inner shell, leaving 4 in the second shell. Therefore, carbon atoms can form up to 4 covalent bonds with other atoms to satisfy the octet rule. The methane molecule provides an example. It has the chemical formula CH4. Each of its 4 hydrogen atoms forms a single covalent bond with the carbon atom by sharing a pair of electrons. This results in a filled outermost shell. Hydrocarbons. Hydrocarbons are organic molecules consisting entirely of carbon and hydrogen, such as methane, CH4, described above. We often use hydrocarbons in our daily lives as fuels, like the propane in a gas grill or the butane in a lighter. The many covalent bonds between the atoms in hydrocarbons store a great amount of energy, which releases when these molecules burn oxidize. Methane, an excellent fuel, is the simplest hydrocarbon molecule, with a central carbon atom bonded to 4 different hydrogen atoms, as figure 2.21 illustrates. The shape of its electron orbitals determines the shape of the methane molecule's geometry, where the atoms reside in 3 dimensions. The carbons and the 4 hydrogen atoms form a tetrahedron, with 4 triangular faces. For this reason, we describe methane as having tetrahedral geometry. Methane, the simplest hydrocarbon, is composed of 4 hydrogen atoms surrounding a central carbon. The bonds between the 4 hydrogen atoms and the central carbon are spaced as far apart as possible. The resulting shape is tetrahedral, with hydrogen atoms projecting upward and off to 3 sides around the central carbon. Figure 2.21 methane has a tetrahedral geometry, with each of the 4 hydrogen atoms spaced 109.5 degrees apart. As the backbone of the large molecules of living things, hydrocarbons may exist as linear carbon chains, carbon rings, or combinations of both. Furthermore, individual carbon-to-carbon bonds may be single, double, or triple covalent bonds, and each type of bond affects the molecule's geometry in a specific way. This 3-dimensional shape or conformation of the large molecules of life, macromolecules, is critical to how they function. Hydrocarbon chains. Successive bonds between carbon atoms form hydrocarbon chains. These may be branched or unbranched. Furthermore, A molecule's different geometries of single, double, and triple covalent bonds alter the overall molecule's geometry, as Figure 2.22 illustrates. The hydrocarbons ethane, ethene, and ethyne serve as examples of how different carbon-to-carbon bonds affect the molecule's geometry. The names of all three molecules start with the prefix eth, which is the prefix for two carbon hydrocarbons. The suffixes ane, ene, and un refer to the presence of single, double, or triple carbon-carbon bonds, respectively. Thus, propane, propene, and propane follow the same pattern with three carbon molecules, butane, butene, and butene for four carbon molecules, and so on. Double and triple bonds change the molecule's geometry. Single bonds allow rotation along the bond's axis, whereas double bonds lead to a planar configuration and triple bonds to a linear one. These geometries have a significant impact on the shape a particular molecule can assume. Methane, the simplest hydrocarbon, is composed of 4 hydrogen atoms surrounding a central carbon. The bond between the 4 hydrogen atoms and the central carbon spaced as far apart as possible. This results in a tetrahedral shape with hydrogen atoms projecting upward and off to 3 sides around the central carbon. Ethane is composed of 2 carbons connected by a single bond. Each carbon also has 3 hydrogen atoms connected to it. The hydrogens are spaced as far apart from each other and from the other carbon, so again, the shape is tetrahedral. Ethene, like ethane, is composed of 2 carbon atoms, but in this case the carbons are connected by a double bond. Each carbon also has 2 hydrogen atoms connected to it, for a total of 3 bonds. The 3 bonds are spaced as far apart as possible around carbon, which means they are all on the same plane and pointing off in 3 directions. As a result, the molecule is planar or flat. Figure 2.22 When carbon forms single bonds with other atoms, the shape is tetrahedral. When 2 carbon atoms form a double bond, the shape is planar or flat. Single bonds, like those in ethane, are able to rotate. Double bonds, like those in ethene, cannot rotate, so the atoms on either side are locked in place. Hydrocarbon rings. So far, the hydrocarbons we have discussed have been aliphatic hydrocarbons, which consist of linear chains of carbon atoms, and sometimes they can form rings with all single bonds, as shown in Figure 2.23 in the examples of cyclopentane and cyclohexane. Another type of hydrocarbon, aromatic hydrocarbons, consists of closed rings of carbon atoms with alternating single and double bonds. We find ring structures in aliphatic hydrocarbons, containing only single bonds between carbons, like the cyclohexane's structure, aliphatic, compared to a ring structure of benzene, aromatic, with alternating single and double bonds in the ring in Figure 2.23. Examples of biological molecules that incorporate the benzene ring include some amino acids and cholesterol and its derivatives, including the hormones estrogen and testosterone. We also find the benzene ring in the herbicide 24D-benzene is a natural component of crude oil and has been classified as a carcinogen. Some hydrocarbons have both aliphatic and aromatic portions. Beta-carotene is an example of such a hydrocarbon. 4 molecular structures are shown. Cyclopentane is a ring consisting of 5 carbons, each with 2 hydrogens attached. Cyclohexane is a ring of 6 carbons, each with 2 hydrogens attached. Benzene is a 6-carbon ring with alternating double bonds. Each carbon has 1 hydrogen attached. Pyridine is the same as benzene, but a nitrogen is substituted for one of the carbons. No hydrogens are attached to the nitrogen. Figure 2.23 carbon can form 5 and 6-membered rings. Single or double bonds may connect the carbons in the ring, and nitrogen may be substituted for carbon. Isomers, the 3-dimensional placement of atoms and chemical bonds within organic molecules, is central to understanding their chemistry. We call molecules that share the same chemical formula but differ in the placement, structure of their atoms and/or chemical bonds isomers. Structural isomers, like butane and isobutane in Figure 2.24a, differ in the placement of their covalent bonds. Both molecules have 4 carbons and 10 hydrogens, C4H10, but the different atom arrangement within the molecules leads to differences in their chemical properties. For example, butane is suited for use as a fuel for cigarette lighters and torches, whereas isobutane is suited for use as a refrigerant and a propellant in spray cans. Geometric isomers alternatively have similar placements of their covalent bonds, but differ in how these bonds are made to the surrounding atoms, especially in carbon-to-carbon double bonds. In the simple molecule butene, C4H8, the two methyl groups, CH3, can be on either side of the double covalent bond central to the molecule, as Figure 224b illustrates. When the carbons are bound on the same side of the double bond, this is the cis configuration. If they are on opposite sides of the double bond, it is a trans configuration. In the trans configuration, the carbons form a more or less linear structure, whereas the carbons in the cis configuration make a bend, change in direction of the carbon backbone. Visual connection. Part A shows butane and isobutane are structural isomers. Both molecules have 4 carbons and 10 hydrogens, but in butane the carbons form a single chain, while in isobutane the carbons form a branched chain. Part B shows cis-2-butene and trans-2-butene each consist of a 4-carbon chain. The two central carbons are connected by a double bond, resulting in a planar or flat shape. In the cis isomer, both terminal uppercase C uppercase H subscript 3 baseline groups are on the same side of the plane, and 2 hydrogen atoms are on the opposite side. Imagine a person with arms stretched out and upwards and legs spread apart, with a glove on the left hand and a sock on the left foot. This represents a cis configuration. In cisbutene, the terminal upper C upper H subscript 3 baseline groups are on opposite sides of the plane. Now, imagine a person with outstretched arms and legs, but this time with a glove on the left hand and a sock on the right foot. This is what a trans configuration looks like. Part C shows 2 enantiomers, each with different arrangement of hydrogen, bromine, chlorine, and fluorine around a central carbon. The molecules are mirror images of one another. Figure 2.24, we call molecules that have the same number and type of atoms arranged differently isomers. A. Structural isomers have a different covalent arrangement of atoms. B. Geometric isomers have a different arrangement of atoms around a double bond. C. Enantiomers are mirror images of each other. Which of the following statements is false? Molecules with the formulas CH3CH2COOH and C3H6O2 could be structural isomers. Molecules must have a double bond to be cis-trans isomers. To be enantiomers, a molecule must have at least 3 different atoms or groups connected to a central carbon. To be enantiomers, a molecule must have at least 4 different atoms or groups connected to a central carbon. In triglycerides, fats, and oils, long carbon chains known as fatty acids may contain double bonds, which can be in either the cis or trans configuration, as Figure 2.25 illustrates. Fats with at least one double bond between carbon atoms are unsaturated fats. When some of these bonds are in the cis configuration, the resulting bend in the chain's carbon backbone means that triglyceride molecules cannot pack tightly, so they remain liquid oil at room temperature. Alternatively, triglycerides with trans double bonds, popularly called trans fats, have relatively linear fatty acids that are able to pack tightly together at room temperature and form solid fats. In the human diet, trans fats are linked to an increased risk of cardiovascular disease, so many food manufacturers have reduced or eliminated their use in recent years. In contrast to unsaturated fats, we call triglycerides without double bonds between carbon atoms saturated fats, meaning that they contain all the hydrogen atoms available. Saturated fats are a solid at room temperature and usually of animal origin. Oleic acid and aleatic acid both consist of a long carbon chain. In oleic acid, the chain is kinked due to the presence of a double bond about halfway down, while in aleatic acid, the chain is straight. Figure 2.25, these space-filling models show a cis-oleic acid and a trans-aleatic acid fatty acid. Notice the bend in the molecule caused by the cis configuration. Enantiomers. Enantiomers are molecules that share the same chemical structure and chemical bonds, but differ in the 3-dimensional placement of atoms so that they are non-superimposable mirror images. Figure 2.26 shows an amino acid alanine example, where the two structures are non-superimposable. In nature, the L forms of amino acids are predominant in proteins. Some D forms of amino acids are seen in the cell walls of bacteria and polypeptides in other organisms. Similarly, the D form of glucose is the main product of photosynthesis, and we rarely see the molecule's L form in nature. Molecular models of D and L-alanine are shown. The two molecules, which contain the same number of carbon, oxygen, hydrogen, and nitrogen atoms, are mirror images of one another. Below the images, a left hand is shown near the L isomer, and the right hand is shown near the D isomer. Figure 2. 26 enantiomers are molecules that are mirror images of each other and are non-superimposable. The LD naming system is from the Latin words for left and right, levis and dexter, respectively. This example shows the L and D isomers of the amino acid alanine. Credit: Rao A. Hawkins, A. Fletcher, S. and Ryan K. Department of Biology, Texas A&M University. Functional groups. Functional groups are groups of atoms that occur within molecules and confer specific chemical properties to those molecules. We find them along the carbon backbone of macromolecules. Chains and/or rings of carbon atoms with the occasional substitution of an element, such as nitrogen or oxygen, form this carbon backbone. Molecules with other elements in their carbon backbone are substituted hydrocarbons. The functional groups in a macromolecule are usually attached to the carbon backbone at one or several different places along its chain and/or ring structure. Each of the four types of macromolecules, proteins, lipids, carbohydrates, and nucleic acids, has its own characteristic set of functional groups that contributes greatly to its differing chemical properties and its function in living organisms. A functional group can participate in specific chemical reactions. Figure 2. 27 shows some of the important functional groups in biological molecules. They include hydroxyl, methyl, carbonyl, carboxyl, amino, phosphate, and sulfhydryl. These groups play an important role in forming molecules like DNA, proteins, carbohydrates, and lipids. We usually classify functional groups as hydrophobic or hydrophilic, depending on their charge or polarity characteristics. An example of a hydrophobic group is the nonpolar methyl molecule. Among the hydrophilic functional groups is the carboxyl group in amino acids, some amino acid side chains, and the fatty acids that form triglycerides and phospholipids. This carboxyl group ionizes to release hydrogen ions, H+, from the COOH group, resulting in the negatively charged Cu group. This contributes to the hydrophilic nature of whatever molecule on which it is found. Other functional groups, such as the carbonyl group, have a partially negatively charged oxygen atom that may form hydrogen bonds with water molecules, again making the molecule more hydrophilic. Table shows the structure and properties of different functional groups. Hydroxyl groups, which consist of uppercase O uppercase H attached to a carbon chain, are polar. Methyl groups, which consist of 3 hydrogens attached to a carbon chain, are nonpolar. Carbonyl groups, which consist of an oxygen double bonded to a carbon in the middle of a hydrocarbon chain, are polar. Carboxyl groups, which consist of a carbon with a double bonded oxygen and an upper O upper H group attached to a carbon chain, are able to ionize, releasing H-positive ions into solution. Carboxyl groups are considered acidic. Amino groups, which consist of 2 hydrogens attached to a nitrogen, are able to accept H-positive ions from solution, forming H subscript 3 baseline positive. Amino groups are considered basic. Phosphate groups consist of a phosphorus with 1 double bonded oxygen and 2 upper O upper H groups. Another oxygen forms a link from the phosphorus to a carbon chain. Both upper O upper H groups in phosphorus can lose an H-positive ion, and phosphate groups are considered acidic. Sulfhydryl group has an uppercase S uppercase H group bonded to a carbon chain. The bond is polar due to the small difference in electronegativity of sulfur and hydrogen. Figure 2. 27. These functional groups are in many different biological molecules. R, also known as R group, is an abbreviation for any group in which a carbon or hydrogen atom is attached to the rest of the molecule. Hydrogen bonds between functional groups, within the same molecule or between different molecules, are important to the function of many macromolecules and help them to fold properly into and maintain the appropriate shape for functioning. Hydrogen bonds are also involved in various recognition processes, such as DNA complementary base pairing and the binding of an enzyme to its substrate, as Figure 2.28 illustrates. Molecular models show hydrogen bonding between thymine and adenine, and between cytosine and guanine. These 4 DNA bases are organic molecules containing carbon, nitrogen, oxygen, and hydrogen in complex ring structures. Hydrogen bonds between the bases hold them together. Figure 2.28 hydrogen bonds connect 2 strands of DNA together to create the double helix structure.